everybody. The pink sheet on the warm-up question. This is a antibiotic. It's a fluoroquinolone. It's like a third-generation antibiotic. Question: if you reacted this compound with chlorine, maybe a Lewis acid such as AlCl3, would the chlorine go here to give this drug, or would it go more likely to go there to give some other compound? Well, what type of directors do we have on this screen? We have 4 groups. Hopefully by the end of the day you'll be able to answer that question. We'll get to Frito Crafts today, which was the one you printed out on your own, I believe. Okay, let's see where we left off at. We're looking at directing effects. Groups 1 through 3 are what type of directors?
Ortho and para
Directors. Ortho para. Group 4 is a meta director. Resonance structures show you why these direct this way. For example, thiamine, if you look at your mechanism, it's the same old mechanism. EAS is one of the mechanisms that we looked at so far. Okay, you ought to be able to show all of this yourself. If the electrophile is added ortho, you get resonance structures, and you get this guy, and the plus is right here where the methyl is, that's particularly stable. You also get the plus where the methyl is if the electrophile is added para to the methyl. You do not get that when it adds meta. The plus never falls where the methyl is if you do a meta reaction. This is why ortho and para is preferred, because your intermediate is more stable with ortho and para. I also show this with the other groups. Now, methyl stabilizes by induction. There was no resonance there, it's just induction, like a tertiary carbocation. Something like an amino with a lone pair, if the cation falls here, you can do more than just say it's stabilized by the methyl. You can actually do resonance structures. If you do resonance, you can get the additional resonance structure, which illustrates why this pathway is more stable. Here are 4 resonance structures for the intermediate. Which one's the major resonance structure?
Your right hand.
The one in the box. Why?
Most charges and most bonds.
More bonds.
Yeah.
Yeah, that one has more bonds. Even though the positive is on nitrogen, it has more bonds. We've seen many examples like that. You also get that very stable resonance structure if the electrophile is added para. You've got to be able to do this. You've got to sit down, do your mechanism, do your get to this point, show your resonance. You've got to practice all through this. Boom. Resonance structure. Extra stabilization. You do not get that if the reaction goes meta. Thus, the reaction prefers one of these, ortho or para. At the same time, if we look at something like a group 4, like a nitro or a carbonyl, same exact structures. Here we got the plus next to the group. But in this case, this is bad, because you got a plus right next to a positive nitrogen. You're forming a plus right next to an electron poor atom. That's not a good situation. So that's not a stabilizing effect here. It's actually a destabilizing effect. Same thing down here. If you do a para attack, you get the plus right here. It's a destabilizing effect. The reaction goes meta. Why? Not because it's so much better, but because in this case, these are worse off because of these. So it goes meta. Any questions about those? You gotta sit down and you gotta work through, you gotta practice drawing your mechanism, your resonance structures, and see what's going on there. There's also some text that may help explain that. This is from another textbook, that's from the Smith textbook. Any questions about those resonance structures? Yes?
What if you have multiple substituents, then like do you do like different combinations of the resonance structures? Does that count as like one resonance structure or like
You want to maybe add them up? Let's talk about if you have multiple substituents. The directing effects would be additive. You've been looking ahead?
no?
Okay, here's an example of reinforced direction. The two groups are going to reinforce each other and get to one answer. Okay? What if you try to chlorinate? This is good. This is standard chlorination conditions, right? Chlorinating an aromatic ring by an ES mechanism. What if you try to chlorinate? What do you want to call this compound? Well, it's got two common names: thiamine benzoic acid. It's probably called 4-methylbenzoic acid or paramethylbenzoic acid. Reasonable name. What if you try to chlorinate it? Is the chlorine going to go ortho to the methyl or ortho to the carboxylic acid? It's only got two choices. Because that's the same, that's the same. Where's it going to go? Well, what type of director is the methyl? Ortho-para. The para position is already blocked or something's already there. Now you could do some interesting chemistry where you maybe add something here and you replace that group. That's going to be odd, unique. For us, especially at the introductory look at it, we're going to say that's blocked and this could go here. So this would direct ortho. All right? What type of director is that? That's meta. So, okay, let's do it up here where the line is drawn. Methyl directs here. Where does this direct? Same place. So it's reinforced. Okay? Ortho to this, meta to that. It's reinforced. And so you get the chlorine added ortho to the methyl, ortho to the methyl. Okay? Or up here it's the same product. So that's where the two groups reinforce each other and the outcome is clearly there. Question?
I was just about to ask if it mattered which side it was on, but you said it didn't.
No, if you name it, it's the same name. It's the same compound as the chlorines here or here. Well, if you name it, it's the same exact name. It would be 3-chloro-4-methylbenzoic acid. Either way you draw it. Okay. Here's some examples where you have opposing direction, conflicting. How do you deal with that? Well, look at this compound. What do you want to call that compound? Para-ethyl anisole. Yeah? 4-ethyl anisole. Okay. What if you sulfonate it? Standard sulfonation conditions. What type of directors is this? They're both ortho-para. So this directs here, this directs here. So where does it go? Well, the answer is the strongest donator typically directs. Okay? The strongest activator. Which one is the stronger activator? Methoxy or ethyl? Methoxy, that's group 1. Strong activator. This is going to be a group 2, a mild activator because it's just induction. So this guy's going to win out and it's going to go ortho to that guy. It rules. Because if you do your resonance, your intermediates and do your resonance structures, you'd rather have positive fall here and do resonance from here than positive fall there. You'd have to look back through there and see that the positive, a reaction adding the group here, the positive would indeed fall there. So the strongest activator wins out. It's going to go ortho to that group, and so if you sulfonate, you're going to get this guy here as your major product. Now, it doesn't mean you might not get some here. That would be minor product, but typically you're asked to say what is going to be the major product. So that's a clear winner there, even though they were sort of opposing. What about down here? What's the name of that compound? Well, you got two common names. Depends on which go. You can call it 4-methoxyphenol. Phenol, paramethoxyphenol. Probably what it's called. Because the phenol is probably going to take precedence, but don't worry about that. Okay, they're both ortho-para directors. So which one wins out? Stronger activator. Well, they're both group 1. So which one's a stronger activator? You might make an argument for one over the other, but it's not going to be clear. Here, they're both similar activators. You're going to probably get more of a mixture here. You're going to get ortho to the methoxy, but also ortho to the phenol. And it's going to be two major products. If you do this reaction in the lab, you're probably going to get two products, and you're probably going to have to do a good bit of work to purify them and separate them. Question?
Did you ever distinguish between group 2A and 2B for alkyl and conjugated pi bonds?
In terms of what?
In terms of like if you would get two products or just one major product? If you're like
No,
directly
I would just
comparing-
probably call them both group 2.
Okay.
In terms of their activation, yeah, I don't, they're too close, too similar. Okay, what about down here? Metachlorobenzonitrile. Was benzonitrile one to learn? I don't think it was. It's called benzonitrile. This would be metachlorobenzonitrile. Bromination, where's it going to go? Cyano group, what type of director? Obviously meta. Well, you know why it's meta, right? The carbon is electron poor, okay? Chlorine, orthopara. So where's it going to go? Meta would be where? Here? Orthopara would be here, here, or here. So it ain't reinforcing. But which one directs? What did we say above?
Chlorine.
The stronger activator. Now chlorine is not an activator, but it's stronger than cyano. So get rid of that. It's going to direct. So is it going to go ortho or para? Okay. I showed all three. This is ortho to the chlorine there or there. Now in this case, they're not the same because these are not the same compounds. The ortho positions are not the same here. Or it could go para. Now of these three, which one do you think might be preferred, or could you give an argument for which one might be preferred?
The middle one.
What do you see about this guy? Putting the bromine between these two groups, that's going to be a little bit sterically congested. Because the complex has to approach here to react. Now these groups may not look that big, but getting in between them is certainly going to be more difficult than maybe over here. Well, that's meta. Here you're only next to one group. Here you're next to two groups. I'd say this is probably least likely. These two are, to me, just as likely. But sometimes we can say that this one may be less likely due to sterics. But all three may be likely major products.
I'm sorry. Wouldn't it most likely be para since the chlorine and the bromine are water?
I can hear you.
Would it most likely be para since the chlorine and bromine like are basically like the most like high priority groups in terms of like size?
What do you mean high priority groups?
Like in terms of like size, they wouldn't be opposite. And they're the largest groups on the largest substituents on the benzene.
Well, how large is the cyano group?
It's not like it.
I mean, to be para, then it had to come in next to the cyano group. Okay, so these fall under what? Not a clear winner. Okay, how about the one down below, which is actually vanillin, which is artificial vanilla. And it's not really artificial vanilla. I mean, if you take natural vanilla, it has this compound. It's linked to some type of saccharide in natural vanilla beans. but if you delink it from a saccharide, this compound also has vanilla taste, and it's called vanillin. And vanillin is in like vanilla wafers or whatever you call them. So I don't know how much. So don't just eat this stuff. Okay, so if you brominate vanillin, what product? What's the product? Can you show the product? And the one below. One below we're nitrating. Where's the bromine going to go?
Mana. You would go mana to the.
Anybody?
I'm just thinking. Ortho to the alcohol.
Do what?
Next to the OH.
Ortho to the alcohol.
Yes, there. Why?
Reinforces two of them there.
The hydroxy directs ortho and para. Well, that's blocked and that's blocked. So hydroxy directs here. The methoxy directs ortho and para. Where does this guy direct? Meta. Okay? So you have two groups directing there. Now, even though this is going to be a more major director, these two conflict. And then we can let that one sort of help decide. Because you can get good resonance structure from here, but since there's conflict, you say, well, let's avoid the bad resonance structure, so meta to there. And indeed, that's where it goes. And I don't know if it's in the lab manual, but at one time I did do the lab where we brominated vanillin. And that is the major product. You can also find it in the literature. But that should be one that is sort of reinforced. These two sort of cancel each other out, and this position is reinforced by these two groups, right? How about that guy? That has two different rings. Which ring looks like it's more reactive? Which ring looks more reactive? The one with group 1 on it. Now you can make an argument about this, but I'm going to not get into that. Here versus a group 2, this ring's more reactive, okay? We're nitrating, right? Standard nitrating conditions. Sulfuric acid. You didn't use sulfuric in lab. You just used nitric acid. If you use sulfuric acid, the reaction is going to be faster, easier. You don't really need it with what you did. If you added sulfuric, the reaction would be sort of very fast. You might get dinitro. It might turn even more orange. So we left out the sulfuric. We just let nitric acid protonate itself. So, the product here would be what? Ortho to this group? In that ring? That would be your product predicted, yeah? How about if you nitrate this guy? Have you ever done that?
That was fluorine.
Oh, I hope so.
Fluorine.
Fluorine? You nitrated fluorine before?
Nitrate.
Yeah.
Yeah, we did.
What do you mean?
Where would the nitro group go?
Up top.
Well, the rings are the same. Let's just focus on this ring. Here, 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 or here.
Top.
Well, we know from lab that it goes here, 2 position. Which, okay, what type of groups are on this ring? What is this?
2.
That's a plain sp3 carbon. That's a group 2.
Yeah.
And we may get to the question you just asked. What type of group is here at this position? Well, it's this ring. I mean, it's sort of bend it down, but this ring is here. So what is this? That's an sp3 carbon. This is a pi system. Both of these are group 2, but this is the induction by alkyl. This is the double bond. The fact that the nitro goes here tells us that which one of these directed? Well, sp3 carbon's an orthopara director. Orthopara. If we go meta to this, what it's doing is going para to this pi system. If you draw resonance structures, you'll see. Now I can maybe also go ortho to this pi system. You might could get nitro here, and that'd be 4 because this is typically 1, 2, 3, 4. That's a minor product. And, you know, at washing you did, or methanol, and then recrystallizing, any of that is hopefully removed. Okay? Think about that. Your two things that are bonded here. Okay. That's it for that. All right, Friedel-Crafts. Anybody got Friedel-Crafts question?
It didn't answer my question. Like, I was wondering, when you want us to draw the resonance structures, if we have multiple substituents, like basically when you draw resonance structures, you're basically moving electrons around, right? So when you have multiple substituents, you can have like, you can move the electrons around like one substituent or like another substituent. So like, if you do it like combinations, does that count as like different resonance structures?
Did you at the beginning say like all?
Like if you want
Did the question say all?
If you want all resonance structures.
Then you would show all.
So like all combinations?
Yeah. Show me what you're asking about. But if it said all, then the answer would be then show them all. I'm not sure if you're looking at a specific question or what, but you could have more than one group conjugated with your cation. Show me an example of what you're talking about.
When we were doing on washing, why did that get rid of the 4 nitrogen and not the 2 nitrogen?
Good question. It depends on how much. If it's only a trace there, I mean, if you got 90% of one and 10% of the other, and maybe the washing gets rid of 10% of this and 10% of this, then you're left. Maybe it gets rid of both of them. But we take that down to 0, and who says we don't lose a little bit of our desired one either? Okay. And I don't know that it's actually formed. I'm just speculating. What I think is also formed is you may get some dinitro. I think it may be nitrated in both rings, and that tends to be more orange colored. And that's that kind of orange, sometimes even darker orange. This gets kind of washed out. There's lots of questions. These are practical things that I can't give you a scientific exact answer on. Okay. All that stuff is just from experience, and it becomes more art than science. Okay, Friedel-Crafts. If you think about it, we know how to put on a halogen onto a ring, a nitro, a sulfonic acid. What else did we put on the ring? I think that's it. It's difficult to put an oxygen directly on the ring, like an OH. We'll see that later with diazonium chemistry. It's difficult to put an NH2 directly on the ring, but we know we can do that by first nitrating and then reducing. But where we're at now is, well, how do you put carbons on the ring? Carbons are put on the ring using Friedel-Crafts chemistry. Friedel-Crafts being two chemists back in the late 1800s. And it allows for carbon-carbon bond formation. For example, you take benzene, we can put on this isopropyl group, and so we made a carbon-carbon bond. And way back in the beginning of organic chemistry, making carbon-carbon bonds was really a big thing because it wasn't easy to do. When Friedel Crafts chemistry came along, it was a very important advance that allowed for synthesis to really blossom. In this case, the electrophile back in your generic mechanism is just going to be a carbocation. So instead of E+, it's going to be C+. Okay? Carbocation. So here's an example reaction. Benzene, we can react with isopropyl chloride or 2-chloropropane, however you want to call it. A Lewis acid. We can get this plus HCl. Mechanism. How do you make carbocations? Well, we made plenty of carbocations before, and we'll actually review some of that below. However you can make a carbocation, you can do this chemistry. Commonly, though, is to use your alkyl halide. How can we make this ionize off? Well, in organic 1, we just maybe heated it and said it's going to ionize off. Then we showed we complexed it with something to help it ionize off. We actually did a chemical test in organic 1 where we used this to... What did we do? Give it precipitate?
Silver chloride?
Silver chloride, right. It complexed with silver and then it ionized off, made silver chloride. Okay, in this case, we're going to use a more traditional Lewis acid. These electrons here. Just like if this was this, right? Didn't we do the same thing with like chlorine? Yeah, same thing. That gives, chlorine is now complex with the aluminum. That's now minus, and the chlorine is now plus. Now, when the chlorine complex, we then attack the chlorine and kick that one off. Here, we're actually going to make a carbocation. This is going to leave. This chlorine's like, hey, I don't like being plus. Carbon, I'm sorry, I'm taking the electrons. And when it takes the electrons, what do we get? We get our carbocation plus that anion. This is how we get to our carbocation, complexing, okay? It's a lot like with alcohols, which is listed below, we protonated and then ionized. Here we're complexing, then ionizing. Now that you have our carbocation, it's just like E+, and we're off to the races. High electrons attack. What does that give? It gives new bond. There's an H there, a carbocation here, boom, boom. Because electrons wouldn't make the bond, leaving that as a cation. Okay? There's no bond up here. The electrons went and bonded to the carbocation. We made that bond, carbocation, resonance stabilized. You've got to be able to show your resonance. If there were additional groups on the ring, you would consider, can you show resonance from using those groups? Even if it was multiple groups. That's your rate determining steps at formation of the sigma complex. It's the same old mechanism, right? The only thing new here is just forming a carbocation by this complexation. What do we do next? Something takes the H and reform. What do you want to take? This guy can be expelled. The aluminum's like, hey, chloride, I like you, but I don't like being minus. So you and your electrons take a hike. So it shoots them off, and the electrons come over here. These move in here. What do we get? You get a product plus what? Plus HCl plus what? Your catalyst reformed. Same old two-step mechanism once we form our electrophile. So Friedel and Crafts showed this chemistry could work. This reaction would have worked 5,000 years ago. But nobody showed it until Friedel Crafts came along. Okay, this reaction works with primary, secondary, or tertiary halides. Chloro is most common. I used chloro in my example. It does work with bromo. Fluoro and iodo, they're just so uncommon. Maybe probably just stick with chloro and bromo. Chloro by far is the most common because it's cheapest and it works fine, so why would you want to use something more expensive? Question?
When you're drawing the arrow from the ClAlCl3 to the attacking the hydrogen, is that a shorthand of saying like the ClAlCl3 like breaks off first to form HCl and then, or like it breaks off?
This here, you want to just leave it, do something like this, and then this go take the H. I mean, that might be all right. Typically, though, it is shown from, it's actually called a sigma bond, nucleophilic sigma bond.
Okay.
Which, I mean, we've seen nucleophilic pi bonds plenty from alkenes, or nucleophile is a lone pair. You can actually find some reading about sigma bonds being nucleophiles. We'll see this again when we look at sodium borohydride. The halide must be on an sp3 carbon. First off, there should maybe be a question about this up here. Question? Good, good. Why primary? Because we showed a carbocation. Then you're saying, well, primary works, so you're going to make a primary carbocation. Very good. When you're using a primary, it may not actually be forming a cation. It may actually be more like how we did chlorine. If this is complexed, instead of this ionizing off and make cation, it might be that the ring, does something like this, more concertedly. All right? I usually don't get into that because it gets a little convoluted. Typically, you see cations shown here, but you're exactly right. We typically don't want to show primary cation. The alkyl halide. Alkyl halide, typically it does not work when it's sp2 or sp. Because you don't want to make, like these guys, sp2, chlorine on sp2, chlorine on sp2, or even sp. I don't show an example of that. That would have to be something like this, which is more unique. It doesn't work with these guys. Why? Because you don't want to ionize and make a cation on these types of carbons. Carbocations are only made on original tetrahedral carbons, typically. Because such a cation like that is worse than a primary cation. All right? That's worse than just what we call a primary cation. Typically, you don't want to make those at all. So the reaction doesn't work with these types of halides. So, what are other routes to carbocations? Because if you can make a carbocation, you can do this chemistry. Well, you can use alcohols. Now we know we can do this. You can protonate an alcohol, multi-steps. You can protonate, ionize, and you can make a carbocation this way. Okay? You can also do it with a Lewis acid. And with alcohols, BF3 is a common Lewis acid. And so here, you complex with the Lewis acid. That becomes minus, this becomes plus, analogous to protonating. Then this can ionize off, and you get your carbocation that way. So complexing the alcohol with BF3, serving as a Lewis acid. as opposed to doing it with a Bronsted-Lowry proton acid. So either way, so you could devise a reaction where you have your aromatic compound, your alcohol, some BF3, and it goes off. And this is still called a Friedel-Crafts reaction. Traditional is where you use an alkyl halide, but anytime you're using carbocation, it's typically Friedel-Crafts. You can also make carbocations from alkenes, right? We did those in organic 1. Alkene with H+, you can get that cation, right? You just attack, leaving cation right. Remember, cation on left or right? On left, correct? So, just because we learn how to make carbocations in organic 1 doesn't mean we just forget it. What's at the bottom? Of course, if you want to make a carbocation down here, you want to use acids like these as opposed to these. Why not use these as the acid?
Go additional.
Because the halide will attack your cation. You don't want the halide to attack, you want the aromatic ring to attack. Okay? Now, could water attack? These are typically aqueous. That might be dry. But if water attacked, that would be just like our good old hydration of an alkene. Yes, possibly water could attack. And if it did, you might get this alcohol. But guess what? Then you could protonate the alcohol and you can ionize and you can reform the cation. Basically, everything's in equilibrium. And eventually, the ring might start attacking the cation. And once the alkyl group gets on the ring, the equilibrium can't go back because you're not going to eliminate the alkyl from the ring. You guys often ask, well, why can't water add here? Yeah, it can. Why can't this happen? I'd say it probably does. But this can happen too, and you got to keep in mind, sometimes everything's in equilibrium. Okay. Friedel-Crafts does have some limits or problems. And to understand the problems, you have to understand directing effects, activating effects. That's why we covered the activation effects first, before looking at Friedel-Crafts. Friedel-Crafts fails, it does not work, if you have strongly deactivating substituents. And the strongly deactivating substituents, that's group 4. And group 4 are also known as what? Metadirectors. So that's another way of saying strongly deactivating, okay? Because this means the same thing. Friedel-Crafts doesn't work if you have a metadirector on the ring. Because it deactivates the ring too much. Bromination will work. Sulfonation will work. But for some reason, Friedel-Crafts typically does not work. Why? Well, you can do some calculations, you might find out why. Or we can just try to call up Mother Nature and say, hey, why do you allow bromination to work with a metadirector but not Friedel-Crafts? It fails. For example, you try to take nitrobenzene and do a traditional Friedel-Crafts, just like we did on our example, you're not going to get a reaction. This ring is apparently not reactive enough to react with a carbocation. You can brominate nitrobenzene. And if you brominated it, what would you get? Yeah. Metabromo-nitrobenzene. I mean, that will work.
Do you like really heat if you don't?
Yeah, it may require a certain amount of heat. It's not going to be as easy as brominating phenol. So, and actually, we don't talk much about solvents. Nitrobenzene is often used as a solvent for Friedel-Crafts reactions. because it doesn't react, even though it's an aromatic. And if you think about it, why would we want to use maybe acetone for Frito-Crafts, or ethanol, or many other solvents?
Because
And these are two common solvents.
HCl is produced.
Group 1 activators, you don't want your solvent to be part of the reaction.
No, but HCl is produced, and you can protonate that.
Well, you got a Lewis acid. What's to keep this from complexing with the aluminum? What's to keep this from complexing with the aluminum? So you got to be careful. Your solvent, you don't want your solvent to complex with the aluminum. You want that chlorine. I mean, look, that's just lone pairs on a electronegative halogen, which likes to hold its lone pairs. I mean, why wouldn't these lone pairs? These lone pairs. So there's some questions with solvents. Actually, nitrobenzene is a fairly common solvent. I mean, you could start questioning about it up in here. But I'm just letting you know that nitrobenzene is a common solvent. It won't react. Okay, another problem is fails with anilines. You take aniline or substitute an aniline, try to do the reaction, no good. Why?
It's going to complex with the acid.
Well, if we're trying to get these to complex with the aluminum, why would that not complex? Indeed it will, and when it does, what do you get? You get that, and, well, could it still react? Well, the answer is no, because now I refer to number 1. Now your nitrogen is positively charged. Now it's group 4. Complexation makes your nitrogen a group 4, which we talked about last time. And since it's now group 4, since it's now a strong deactivator, I refer you up to number 1. Now, if this is like an OH or an O-methyl, the reaction will work. You're like, well, why come it doesn't complex? Well, maybe it does, but it's in equilibrium. Apparently with the amine, this is formed and it doesn't want to go back because the amine is more basic. It will work with these. It'll work with any group 1 except for anilines, really. Question?
So if it was put in acidic conditions, would it work?
Typically no, but under acidic conditions, this is going to have the third H positive. No. But this is acidic conditions. That's because, are you talking about a Bronsted-Lowry acid acidic conditions or
Yeah.
Lewis acidic
Or
conditions?
Ross?
Okay, well that's different. This is Lewis acidic conditions. Lewis acid. I knew you meant Bronsted-Lowry, but this is also considered acidic. Just Lewis. Lewis acidic. Also, what are carbocations prone to doing? Did we ever discuss that in Organic 1? Yeah, I think we said that carbocations are always prone to rearranging. Okay, and we don't ever forget that, right? All right. So if you try to do and this also has the dang thing of, well, is it going to be a primary cation? We might have to show it. I don't know if my pen will work, but if you try to do a Frito-Crafts here, you only get 35% of this. I mean, if you complex here and ionize, it looks like you're going to get this cation. All right, shield your eyes. And then if the ring attacks here, 1, 2, 3, 4, you get this product after it does its thing. But if you were to get this from some magical reason, do you think it could perhaps rearrange? Hydride shift, right? Then we get this cation, and this would be much better. Now do we see how we might get this product? The ring has attacked the secondary because a hydride shift took place. And look at your outcome. Which is a major product? Actually, this is the major product. And like we said in Organic 1, if you can do a rearrangement, typically do that. We're going to call the rearranged the major product. Okay? So this does, if we have to, if this is all we're going to talk about, it does involve making a primary cation first. All right? Bad though, right? Bad. Everybody see that? Now, I label this as A, because later on we will make A in a much better yield. We'll do a two-step route to make this, and I'll refer you back to this, which was, here if you tried to make it directly using this, it would not be the major product, you would get the rearranged product. Okay? Question?
But it's still Frito Craft's chemistry, right? Because you're still
Yes.
making a C. Okay.
Yes.
So then there's no real issue. It just will.
No, the issue is if you wanted to make A,
Oh, okay.
it would be a modern product here.
Okay. I got you.
If you wanted to rearrange, then it's no issue. That's, yeah. That's the way I should have set it up. A is maybe what we were looking for, but it's going to rearrange. Another problem. Again, may not be a problem if you want it, but it's polyalkylation. So you do this here. This is our model reaction we did. Make isopropylbenzene, which may be called cumene. There's lots of common names. You don't need to know it. I think it's called cumene. I'll call it isopropylbenzene. It can react again. Let me ask you, which is more reactive towards EAS? Starting material or product? Product has an activating group on it. By induction, a group 2 activator. The product's going to be more reactive. So our reacting species is this. Let's say it's going 10%. We got 10% of this, 90% of this left. Well, this guy, as it builds up, is going to start reacting. You can't say, hey, once we make you, we want you to just sit still and don't do anything. It won't listen to you. It's going to say, hey, I'll go react, and I can react faster than that guy. And then when this reacts, you're going to have two. Now I showed para, it may also react ortho. But now we have two activators. Now it's more reactive than that. And you get a third one. And now you got 3 activators. And you keep on. Now you could put 6 on there. Eventually it may slow down because of sterics. Once you get 3 or 4, then having the other one come in between the existing groups may slow it down and make one of these back over here faster. In the end, it's very hard to do it to get high yield here. Hard to get high yield because you typically start getting mixtures of these. Okay? Now, rearrangements and polyalkylation, we can solve this problem on the next page. And that's when we look at Friedel-Crafts acylation. Acylation is going to give us a ketone on the ring. It's still a carbon. The carbon is in a form of a ketone. Okay. I remember the Wonder Twins.
What? Yeah.
What?
Wonder Woman powers
American powers activated.
Okay, I didn't know if that ended in like 1985
It
or
did
something.
actually, I'm old.
In the form of a carbonyl, right? I mean, they used to say in the form of an ice bucket or something. In the form of an eagle. This is in the form of a carbonyl, all right? And a carbonyl is typically called an acyl group. Acyl. This comes from your chlorine being on an acyl. Or also, like it'd be called an acyl chloride. Okay? If you use an acyl chloride, they may also be called like an acid chloride. We'll see these when we get to acid chemistry during test 3. Okay? And it's going to be a very similar mechanism. Okay? Please do it on your own. We'll look at it next time. Complexing, ionizing. Racurial make a cation that we saw before during mass spec. Mass spec of a carbonyl, the carbonyl cation, which was called what?
Acylium ion.
Acylium ion. We're going to make acylium ions here. Okay? Please look at this.
Lab report.
Yes, thank you. We're not going to delay any more on this. If Monday Lab would please pass them